In this topic, I want to discuss iteration. Specifically, I want to discuss how iterating at the Python level might hurt or might help us for our analyses, especially in terms of speed. Let's talk about crossing the domain first. If you're not familiar, when we say crossing the domain, all we're talking about is the actual lifting of pandas or NumPy values back into the Python layer, performing compute, and then trying to shove those values back into the NumPy and D layer. Every time we cross that boundary from NumPy to Python or pandas to Python and vice versa, we incur a good amount of overhead that's going to cost us some performance on our speed. And so what we're doing here is we have some values in a Python list. We have some values in a NumPy and D array. We're going to be calling the NumPy sum on these values and the regular just built-in Python sum of these values. We're going to grab the Cartesian product of these things and we're going to look at these timings. So when I use the NumPy sum on just the Python list, we have relatively slow performance. The fastest performance, of course, since we're working with actual numbers, integer data, well, the best performance is no surprise that when we apply a NumPy ufunc onto a NumPy array, we actually see great performance here. Now, the interesting thing that I want to draw your attention to is when we apply the Python sum onto a list of Python values, we actually get quite good performance. Remember, there's 100,000 integers here that we're actually summing up. And so we get quite good performance for the Python values on a Python function. But when we switch things up, when we cross that domain and we look at the NumPy sum on the Python values or the Python sum on the NumPy values, we pay the price of crossing the domain. And so we always want to work within the domain, even if that means all we're doing is just staying within Python, because that will have the best performance for us. So where do we end up crossing the domain in pandas? We end up crossing the domain in pandas whenever we use things like .apply with a lambda or a UDF. And just very quickly, if you're not familiar, UDF is a user-defined function. Not necessarily a lambda, but it's most often a lambda function. But it can also be previously defined functions. One of the common things that I'll do, if I'm running some statistics, I'll do something like this. On stats models formula API. I will actually grab import OLS just like this. I'll actually create my linear model like this, maybe Y predicted from some X values here, and then I'll load in, or I'll keep my data frame, I'll keep my data dynamic, and I'll wrap this into a fit function. And I'll pass, maybe this will be my string representation of my model, this will be my data frame, and then I'll return, the fitted model here. So data equals df. And the reason I do this is sometimes I want to actually fit, a single linear regression per maybe group of data. I don't want to fit it to the whole data frame in its entirety. And so I'll do something like this, model is this, and then I'll return, this is the fit object. So I'll just return the .fit right away. Then at this layer, I'll take my data frame and maybe I'll do a group by if I had some groups here. And I'll do this .apply. And I'll pass fit and I'll say model equals Y predicted from some X's. And this way I can have a dynamic model that I can keep changing. And so I would get rid of this and I would just swap this out for the model itself. And so this is how I would fit a linear model to every single group of data that I had within my data frame. But you can see that I'm calling a user-defined function, something that I created called .fit or called fit, and it's creating a single ordinary squares model and providing that fit. This is all at the Python level. So I'm effectively iterating over every group and calling an arbitrary Python function on that group of data. This is where we end up crossing the domain. Especially, thank goodness stats models is actually using each NumPy array to its advantage. But if I ever do something where I'm manually iterating over the contents of each group, or I'm grabbing them and pulling those values into, say, a Python list, that is where I'm especially going to be crossing the domain. So a lot of the dot apply, whether it's a group by dot apply, whether it's a data frame dot apply, but not necessarily, or a series dot apply, that is where you will be crossing domain. So is dot apply always slow? Is it something that I should always avoid no matter what, absolutely every time? Well, let's take a look. Let's take a look at our series dot apply. And what I'm doing here is I'm passing a lambda in, and I'm going to just be multiplying every value by 2. And at this level, I'm just going to use essentially the underlying NumPy operations to just multiply all the values by 2 at the NumPy level or at the pandas level here in this. But what you end up seeing here is that the dot apply in this case is going to be much slower. The series dot apply is anticipating a function that will be called on every single element of that series. Now, this is in a slight contrast to the data frame dot apply. Note that for the data frame dot apply, I am passing a lambda here, and I'm performing v times 2. The data frame dot apply, however, when I look at my timings, is almost 10 times faster than the series dot apply. In fact, the data frame dot apply is very close in terms of speed to both the series reference and the data frame reference, where all I'm doing is just multiplying these values by 2. What's happening here is the data frame dot apply with no additional arguments will iterate at the Python level over every single column of our data frame, and it will call this function onto that column. Now, pandas has fast path detection in here. It will essentially see or try to guess, can this function be called just on the series itself, or does it need to visit every single element of the series? But we do have some manual control over that. We can use apply map in this case, and you can see I lose all of that performance bonus that I was gaining from just the dot apply. Apply map is when you want to take a data frame and call a Python function or call any function on every single element of that data frame. So I'm visiting every cell in this data frame. Apply will be called on every single series that composes or every single column that composes my data frame. So there is a difference here, and you can still get good performance with data frame dot apply and passing in a user-defined function or a NumPy ufunc here. So that is the one thing to watch out for. Even if this data frame doesn't just have a single column to it, even if I make 10 columns to it, you can see that its performance doesn't get much worse in the series. In this case, I'm calling a Python function 10 times, one on each column at the Python level, but I'm not doing that much worse than my series apply, which has to visit every single element of the given series, which has 10,000 elements in it. You'll see, though, that not calling apply or avoiding the apply in this case is going to give me the best performance. So whenever you're working with pandas, always try and think in terms of vectorized operations and how you can perform things without relying on this dot apply. Typically, I would recommend using something like df.pipe. In this case, I can still pass lambdas, I can still do very dynamic things, but I know that I'm going to be operating on the data frame as a whole. And so I can do something like this. Here, my only overhead is the actual calling of this lambda just one time. And I can leave the rest of the work up to the underlying implementations. And so that's the rundown, the difference between .apply map, and .pipe. Now there is one more difference between map and apply, and it's not at the data frame level. The data frame, has .apply, has apply map, it has pipe, almost everything in pandas has pipe, but there is a very stark difference between map and apply at the series level. And so I'll go ahead and show you this. We have .apply with a lambda, we have .map with a lambda. Their timings, .map ends up coming out faster depending on how many times I run this test, but not every single time. Well, it turns out that .map is performing the same thing. If you give it a callable, it's going to visit every single element in that series, and it's going to perform an operation on that. What .map is really designed for, in my opinion, is not arbitrary callables, but mapping values or replacing values in this case. And so I can define a dictionary and I can pass this to series.map. And in this case, anytime I encounter the value 0, I'm going to replace it with 4,000. Anytime I encounter the value 1, I'm going to replace it with 3,000, and so on and so forth. This is extremely useful when working with strings. And I'll give you an example that I use called entity normalization. Say I have messy data. We always are working with messy data. And so sometimes, right, say I have a list of company names. Sometimes, right, it's Google with a capital G. Sometimes it's Google with a space on the end, or sometimes it's a typo Google, things like that. I can do as much string cleaning as I want, but trying to find that specific typo of Google and replacing it with Google can be tricky. And so something that you would probably do is actually start to normalize those entities and capture, right, those typos or those mistakes. And I could do something like this, right? And I could overwrite or replace every time I see a Google with Google. Now, you can also do this, right, with the replace function, and there is a slight difference when it comes to this. The mapper, or the .map with the dictionary approach, I'll show you what this returns. Well, I'll also show you how long it takes to run. Actually runs quite quickly, especially when compared with, right, having a callable. So there is a fast path that Pandas is tapping into in order to perform these replacements and these lookups. Now, the difference here between doing .map and something like .replace is you'll notice that I replaced my values 0 through 2 with the corresponding values looked up from my dictionary. Everything else gets turned into a not a number. And so it's up to me what I want to do with all of these not a numbers. Sometimes, if I'm doing that entity normalization, I want to see, is there anything left over? Have I missed anything? And so that's a very useful time that I can say, okay, if .isNA.any, right, if there's any nans left after I apply my mapping, then let me know, because I want to verify that I've captured everything in this mapping or not. And so this is a useful trick, right, for cleaning up your data and being able to work with it afterwards. And it's implemented in a very fast fashion. Now, there is a similar approach or a similar thing that you can do. Essentially, any mappable object, so this is Pandas series, or even, right, things that implement the dictionary API, the dictionary object models, you can actually pass a default dictionary to the .map function, and you can provide a default. So here, before you saw that I was getting nans wherever there wasn't something that corresponded. With the default dictionary approach, you can see that I'm actually getting zeros here instead. You can see the performance cost, isn't too bad. But one thing that I do want to point out is this. The performance differences, right? We see a good speed up over the regular dict implementation, because you have to think the default dictionary is going to be calling, right, that missing double underscore method every time it fails to look something up. And in this case, we're calling that a lot. So we're calling a Python function actually a good amount of time here. And that's why we see even worse performance between the default dictionary and just an arbitrary lambda. But what we end up doing here, what we can do here to achieve the same result, is actually just to fill the nans afterwards. And in this case, we're still, right, staying within Pandas restricted computation domain to make sure that we receive, right, the same results as we saw in that default dictionary case here. Now, I would need to convert, right, the data type if I wanted to force everything to be an integer, because Pandas does automatic promotion, which is something that's not here to stay, I'm happy to share with you, but we'll get to that later this morning. Let's talk about some iteration here. Iteration is not necessarily the problem. It's when and where you use it. You saw with that data frame.apply, it wasn't too bad because it was just applying across the columns. And usually, not every time for a lot of my ML engineers out there, but usually we have data that is taller than it is wide. And so if we iterate from column to column, we're not paying an extremely heavy price. We also have to consider Pandas' memory layout of all the values. But let's take a look at comparing iter rows to iter tuples to .apply to, well, our benchmark or our reference, right, just a vectorized operation. In this case, I'm going to be adding together all of the values from S0, which is one column in my data frame, to S1, which is the other column in my data frame. What you can see here is that iter rows is extremely slow. Iter tuples is incredibly fast, well, compared to iter rows, and then .apply falls somewhere in the middle. Let's figure out why this might be happening. Iter rows creates a row object, or it creates a pandas series for that row. And so if I were to look at any one of these rows, you see that I end up with this pandas series object. It has an int64 data type, which is nice because I only have integer data in my data frame, and it's actually working to our benefit. So this is a best case scenario for iter rows here.